In this lesson, we want a review of complex numbers. All right, so I want to start out by talking about the imaginary unit I again. So we say I is equal to the square root of -1, and this is used to allow us to simplify when we have the square root of a negative number. So for example, if I had the square root of, let's say, -4, using the product rule for radicals, I could write this as the square root of -1 times the square root of 4, okay? I know that the square root of 4 is 2, so let me just go ahead and put the square root of -1 times 2 like this. And then I can replace the square root of -1, okay, since those guys match up with this I here. Okay, so this can go right there. So this is I times 2, or you just write 2I. Okay, so that's a way to simplify the square root of a negative number. Now also, let me erase all this. We can square both sides and come up with another definition. We could say that I squared is equal to -1. And we're going to use this all the time. Okay. Now, using this imaginary unit, we can form what's known as a complex number. So the complex number in standard form is going to look like this. You're going to have A, which is your real part, plus B, which is going to be the imaginary part, times I, which is the imaginary unit. Okay, so let me label this real quick. This A is called the real part. Okay, and then the B here is called the imaginary part. Okay, now some books will call BI the imaginary part. Just get with your book or your teacher in terms of what they want to do if you get this for vocabulary. Now, in terms of complex numbers, we don't often think about it this way, but if you just had the number, let's say 3, well, 3 is a complex number. Okay, 3 is a complex number because I could always say 3 plus 0i. It's kind of like when you think about 3 as being a natural number, right? It's a whole number, and then it's an integer, and then it's a rational number. And the way you show it's a rational number is you go, okay, well, 3 is equal to 3 over 1, right? Those are the same. So this is, by definition, a rational number. So it's the same kind of trick here where we just say, okay, well, 3 is really equal to 3 plus 0i because this is just 0, and 3 plus 0 is still 3, okay? So this tells me that any real number that I'm working with is also a complex number. So the real numbers are a subset, okay, of the complex numbers. And if you have a complex number, okay, like let's say 4 plus 2i, this is called a non-real complex number. That's how you can differentiate between the two. Also, you can have something that's called a pure imaginary number. Let's say you just had the 2i part. Okay, so this you could write as 0 plus 2i, which is just 2i. This is also a non-real complex number, but a lot of books will call this a pure imaginary number. Okay, let's go ahead and look at some examples. We're just going to fly through these. Again, this is just stuff we've already seen. If you wanted to simplify the square root of something like -147, you would use your product rule for radicals. I would just put this -1 here times, you would try to factor this. Well, 1 plus 4 is 5. 5 plus 7 is going to be 12. I know that 12 is divisible by 3, so 147 will be divisible by 3. And if I divide 147 by 3, I'm going to get 49. So I can put a 3 here, and I can get a square root of 49 here, okay? And this guy is a perfect square. So the square root of 49 is 7. So what I can do here is say that this is equal to square root of -1 times square root of 3, okay? Then times 7. Now this guy right here I can always replace with I. So really I'll end up with just saying that I have 7i, okay, times the square root of 3. So this would be our simplified answer for this square root of -147. Again, 7i times the square root of 3. All right, another similar problem, we have the square root of -180. So for this guy, if I think about 180, I would factor this. So 1 plus 8 is 9. So I know it's divisible by 9. So let me go ahead and put 9 there. And this would be 20, right? So 9 is 3 times 3. Those are prime. 20 is 4 times 5. 4 is 2 times 2. So what I'd want to do, since 9 is a perfect square and so is 4, multiply those together, you have 36. So basically you'd want to write this as square root of -1 times square root of 36 times square root of 5. Okay, so that's going to allow you to simplify. And basically square root of 36 is 6, and square root of -1 is I. So I'm just going to put that we have I times 6, or I should really rearrange this and put 6i, and then just times the square root of 5. Okay, so simplifying these types of problems, very, very simple. This is our answer. Again, the square root of -180. This is going to simplify to 6i times the square root of 5. All right, so additionally, you will see complex numbers when you work with equations such as a quadratic equation, we know that if the discriminant, that b squared minus 4ac part, if that's less than 0, you're going to get complex solutions, okay? So we're going to see that here. So I'm just going to solve this. I'm going to use the quadratic formula. If you want to complete the square, you can do that on your own. So I have 2x squared plus 10x plus 5 equals 8x. I'm going to subtract 8x away from each side to put this in standard form. So this is going to cancel over here and be 0. So I'm going to have 2x squared plus 2x plus 5 equals 0. And basically, I'm going to record the values for a, b, and c. Okay, so what's a? It's the coefficient for x squared. So this guy right here, so that's a 2. And then what's b? It's going to be the coefficient for x to the first power, so that's also a 2. And then what's c? That's going to be your constant term, so in this case, that's 5. Okay, and then you're going to plug in. So x equals, remember this is negative b, plus or minus the square root of b squared minus 4ac all over 2a. Okay, this is something I've memorized throughout the years. If you don't have this committed to memory, it's okay. Something you can really look up quickly. Okay, so I'm just going to scroll down a little bit, and I'm going to plug in. So x is equal to the negative of 2 plus or minus the square root of, you're going to have 2 squared minus 4 times 2 times 5. And all I'm doing is I'm just plugging in. Okay, this is over 2 times 2. So I plugged in for b, a, and c, and that's where we got this from. Now, let's just go ahead and solve this real quick. It's just a matter of punching this into your calculator. So x is equal to negative 2 plus or minus the square root of, you have 2 squared, which is 4, minus 4 times 2 is 8. 8 times 5 is 40. You go ahead and do 4 minus 40. That's going to be negative 36. And you can see because this part right here ends up being negative, you're going to have these complex solutions. Okay. Then this is over the 4 because 2 times 2 is 4. And then the square root of negative 36, you can say that is 6i, right? Square root of 36 is 6, and then square root of negative 1 is I. Let's come down here a little bit, and let's go ahead and say that x is equal to negative 2 plus or minus, I'll put 6i over 4. Now, we can factor out a 2, okay, and make this a little bit better. So let's go ahead and say x is equal to, let me pull this down here a little bit. I'll factor out my 2. I'll have negative 1 plus or minus 3i, okay, then over 4. I'm going to cancel this with this and put a 2 here. So we'll say x is equal to, you have negative 1 plus or minus 3i over your 2. Now, if you want to write this in standard form for the complex number, then you could put this, we'll go ahead and do solution set notation. I'll put negative 1/2, okay, like this. And then I'll go plus or minus, we'll do 3/2 and then times I like this. Okay, so that's your solution set notation. Maybe I can make those brackets a little bit better. Let me try to make this one a little bit better like that. Okay, and of course, this is two different solutions, right? You have negative 1/2 plus 3/2 times I, and then you have negative 1/2 minus 3/2 times I. All right, let's start working on some operations with complex numbers now. So the first thing I'm going to do here is a simple multiplication problem. I'm doing this to draw your attention to a common mistake. So we know with the product rule for radicals, something like square root of a times square root of b, this equals the square root of ab. This only works when they're both not negative, okay? So if you try to do this here, you're going to end up with the wrong answer. So what you have to do when you have negatives involved like this, you have to convert them over, okay? Simplify first, and then go through a multiply. So what I would do here is I would say this is I times the square root of 3, then times, for this one, let me go ahead and write this out. So we'll have 2 times, I'm going to put the square root of negative 1 times the square root of 4 times the square root of 2, okay? Just so you can see what I'm doing. Square root of 4 is 2, so 2 times 2 is 4, okay? And then basically you would have square root of negative 1, which is I. So this becomes 4i times the square root of 2, okay? So from here now, if you multiply, you see that you have I times 4i, which is going to be what? That's going to be 4i squared, okay? Square root of 3 times square root of 2, we can write as the square root of 6. Now, what is I squared by definition? Remember, earlier we said this is negative 1, so you can say you have 4 times negative 1 times square root of 6, which is just going to be the negative of 4 times the square root of 6. Now, you'll notice if you didn't follow this formula, okay, and go ahead and convert this first, you would end up with a wrong answer, right? You would end up with a positive 4 times the square root of 6, which is not the correct answer, okay? So you want to make sure you convert these over, simplify them first before you multiply. Okay, let's look at some addition of complex numbers. Really, really easy topic. To add two complex numbers, so for example, if I have a plus bi, and then I add this to, let's say, c plus di, okay? This is what? Add the real parts, so a plus c, okay? And then plus, you're going to add the imaginary parts. So we'll say b plus d, okay, and this is multiplied by I. That's all it is. If you were subtracting, okay, so if this was a minus, then this would become a minus, and this would become a minus, and that's basically it. Now, when you subtract things away, remember you can do addition of the opposite. So you could always go plus, and then minus like this, okay? So if you want to do that, you can do that. Either way, your answer is going to be the same, okay? So let's go ahead and get rid of this, and let's work on this problem here. So we have 4 plus 2i, plus we have negative 7 plus 7i. Okay, so what do? We add the real part, so 4 plus negative 7. Let me show this. So 4 plus negative 7, okay? And let me put a parenthesis there, and then plus. You add the imaginary parts, so 2 plus 7, so 2 plus 7, okay? Then times I out here. And let's go ahead and simplify this. So 4 plus negative 7 is negative 3. And then plus 2 plus 7 is 9, and then times the imaginary unit I. So this is your answer here, okay? And it's in standard form, so negative 3 plus 9i. All right, for the next problem, let's do a subtraction. So you can do this as addition of the opposite if you want. So I'm just going to go ahead and say this is 7 plus 2i, okay? I'm going to say plus, and I'm going to change the sign of everything inside. It's just like if I put a plus here and a negative 1 outside and distributed this to each term, okay? That's all I'm doing, okay? I think it makes it a little bit simpler. So I'm going to change this to positive 5, and I'm going to change this to positive. I'm going to write a 1 and then times I. Remember, if something's hanging out by itself like x, you can put a 1 in front as the coefficient, okay? So now I can just add. So this will be 7 plus 5, okay? And then plus, you're going to have 2 plus 1, okay, and then times I. So this gives me 12 plus 3i as a result. And again, if you want to do this with subtraction, you can. It's going to look a little bit different. So what you can also do is you can say that you have 7 minus, in this case, this is a negative 5, so be very careful, okay? And then you have plus, you're going to have 2 minus, this is a negative 1, so again, be careful, okay? And then times I here. 7 minus a negative 5 is 12. And then plus 2 minus the negative 1 is 3, and then times I. So same answer either way. I think it's more straightforward if you do addition of the opposite. Let's look at some multiplication. Again, with these type of problems, you can generally use FOIL, okay? And sometimes you'll get longer ones just depending on the situation, but just pretend like you're multiplying polynomials, okay? So I'm going to use FOIL here. So I'm going to do the first terms. Negative 4 times 2 is going to be negative 8. And then my outer, negative 4 times 4i would be minus 16i. My inner, I would do negative 3i times 2. That's minus 6i. And then my last, I would do negative 3i times 4i, which would be negative 12i squared. Okay, so I squared is negative 1, so let's go ahead and replace that. So I'm going to have negative 8, and then I'll go ahead and move this down and say minus 12 times negative 1. Well, negative times negative is positive, so I might as well just say this is plus 12. Okay, and then I have this would be minus 16i, minus 6i. So I can say that's minus 22i. So negative 8 plus 12 is 4. And then we'll say minus my 22i. Okay, so that's going to be my answer there. And I boxed it off a little bit too closely. So 4 minus 22i. All right, so we should know at this point about conjugates. If you have complex conjugates, the formula is a little bit different. So if we have something like a plus b times a minus b, we know this is a squared minus b squared, okay? As an example, let's say I have something like x minus 2, okay? Then I have x, let's say, plus 2. I know this is x squared, which is the first guy, minus 2 squared, which is the second guy, which is 4, okay? I don't need to FOIL this out. That's the quicker way to do it. But if I'm dealing with complex conjugates, the sign is going to change. It's not going to be minus, it's going to be plus. So for example, if I have a plus bi times a minus bi, what happens is a times a is a squared. The outer and the inner are going to cancel. And then the last, you have your minus b squared times I squared. Well, this I squared here is negative 1, and that's what's changing the sign. So you end up with a squared plus b squared, okay? So if I look at this pattern here, I have 4 plus 3i times 4 minus 3i. I can just say, okay, the first guy squared, 4 squared is 16, plus this 3 guy here, the second guy, just the b part, just the imaginary part. So the 3 guy squared, which is 9, so that's 25, okay? This is always going to be just a number. So in this case, it's just going to be 25, okay? Again, if you wanted to go through this the long way, we can. Just for the sake of completeness, we would do first times first. So 4 times 4 is 16. And then the outer would be negative 12i. The inner would be positive 12i, so you see those guys are still going to cancel. Then for the last, you have 3i times negative 3i, so that's minus 9i squared. And again, the I squared here is going to change the sign. And I circled that a little bit too widely. But basically, this is what? This is 16, you might as well say, minus your 9 times negative 1, which is 16 basically plus 9, which again is 25. Okay, let's talk about dividing complex numbers now. So we know that if the imaginary unit I is in the denominator, since I technically is the square root of negative 1, it represents a radical, and it needs to be rationalized, right? So we want to rationalize the denominator when we see this situation. So if I have something like negative 3 minus 4i over 5 plus 4i, what can I do? Remember, we just talked about multiplying by the complex conjugate. If I multiply this by 5 minus 4i over 5 minus 4i, what's going to happen is in the denominator here, I'm going to have a real number now, okay? We don't care what happens in the numerator. We're trying to get the radicals out of the denominator. So in the denominator here, again, I can just take this guy. 5 would be squared. That's 25. Then plus this 4 would be squared. That's 16. So this ends up being 41. Okay, so that's the denominator now. So we're good there. In the numerator, you go through and just do FOIL, right? So negative 3 times 5 is negative 15. The outside would be negative 3 times negative 4i, which would be plus, we'll go ahead and say 12i. The inside would be negative 4i times 5, which would be negative 20i. Let's just go ahead and combine like terms. This would be a negative 8i, so a negative 8i. So I'll put minus 8i there. And then for the last, you have negative 4i times negative 4i. That's going to be plus 16i squared. I squared is negative 1, so let's get rid of this and just change the sign. So basically, I have negative 15 minus 16. So let's say this is negative 31. So the top here is negative 31, and then I'll put minus 8i, okay? Now, of course, if you want to write this in standard form, you want to break this up and say that you have negative 31 over 41. Let me put equals here. So this is the real part, and then we'll put, you can put plus, negative, or you can just put minus. I'll put 8 over 41 like this, okay? Let me make that 1 a little bit better. And then I'll put my I out here, okay? So this is your A, or your real part. And then this is your B, okay, or your imaginary part, okay? Then you have your imaginary unit I. And of course, you could put plus negative there if you want to. That's up to you. If you put minus there, it's really the same thing, so that's why I'm putting that. Okay, let's talk about simplifying powers of I, which is a really easy concept. Once you realize, you go through this little cycle. So I to the first power is just I squared is equal to negative 1. I cubed is I squared times I, right? So this is negative 1 times I, which is negative I. And then I to the fourth power is I squared. Let me make that better. So I squared times I squared, which is basically what? Negative 1 times negative 1, which is 1. Now, using this pattern, it's really easy to rewrite things, okay, in terms of one of these guys right here, and then you're just going to simplify. Okay, you can put that as your answer. So this involves the rules of exponents. So what I'm going to do here is I'm going to look at this right here. So this number is 151, okay? So thinking about what number going down would be divisible by 4. So I just take 151, punch this into my calculator, divided by 4, gives me what? Well, you're going to get 37.75, but I'm going to write this as 37 with a remainder of 3, okay? So basically the 3 divided by 4 is where you're getting the 0.75 from. 37 times 4 is 148. So I can use that to my advantage. I can say, well, this is I to the power of 148 times I to the power of 3. So this is completely legal, right? I basically have just used my rules of exponents. We have I and we have I, so the same base. We would add exponents and we'd be right back to where we started. Now, what I can do, since this number right here is divisible by 4, I can use a little trick and I can say power to power rule, I to the fourth power raised to the 37th power, because again, 148 divided by 37 is 4, so 4 times 37 will be back to 148, right? This is power to power rule. Then times I cubed, okay? Now, why does this work? I to the fourth power, we see over here, is 1. So this guy right here is 1 raised to the 37th power, 1 to the 37th power. 1 to any power is always 1, right? So I can basically just get rid of this and say this is a big fat 1 now, times I cubed, okay? So I've dealt with that. And now I can just go to my little reference here and say, well, what's I cubed? It's negative I, okay? So that's basically what you want to do when you have a problem like this when this guy's positive. All right, let's look at another example. So we have I to the power of negative 38. So there's a really easy way to do this, but let me do it the slow way first. I'm going to write this as 1 over I to the power of 38, okay? And then, of course, I can just do 38 divided by 4 and see where that puts me. It's going to be 9 with a remainder of 2, or 9.5. So really, I could write this. I could say this is equal to 1 over I. I'm going to go ahead and put I to the 4th power raised to the 9th power, okay? Then I'll put times 1 over, we'll go ahead and say I raised to the power of 2, okay? That remainder right there. Now, we know that this guy right here is 1, and 1 to the 9th power is 1. So I can just keep going like this and say this is what? This is 1 times 1 over I squared. I squared is negative 1, so I can say this is 1 times 1 over negative 1. So this just ends up being negative 1, okay? So really easy to simplify this, but this is kind of a long way to do it. The shorter way, if you're working with a negative exponent like this, well, now what I'm doing is I'm thinking about the smallest number that's divisible by 4, okay, that's going to be larger than this number. And I'm thinking about this in terms of its absolute value. So if you think about just the number 38, okay, going up, okay, what's the closest number that's going to be divisible by 4? Well, it's not 39, it's going to have to be 40, okay? So in other words, I would want to multiply this by, I would want to say I to the power of negative 38 times I to the power of 40. That's all I need to do, because what's going to happen here is that I to the power of 40 is just 1. I can multiply anything by 1, it's unchanged. So this is going to end up telling me that I have what? I to the power of negative 38 plus 40, okay, which is I to the power of 2, or I squared, which by definition is negative 1. So for me, this is a little bit quicker if I get this type of problem, but you can do it the other way if you'd like. All right, so the last thing I want to do is review a few things about the complex plane. So let's say we wanted to graph something like 5 minus 7i. What we do is set up a little complex plane. So instead of having x and y, we now have the imaginary, okay, which is vertical, and the real, which is horizontal. Okay, so before this was x and this was y. Now this is imaginary, this is real. Okay, so if I have something like 5 minus 7i, well, again, this is the real part. We talked about this earlier. And then this right here, the 7 is the imaginary, okay, part. So all I need to do is move 5 units horizontally. Okay, 5 is positive, so I'm moving to the right. So I'm going to go 1, 2, 3, 4, 5. Okay, so right there. And then I want to move 7 units down vertically. Okay, so I want to move 7 units on the imaginary axis going down because it's negative 7. So 1, 2, 3, 4, 5, 6, 7, and it's going to put me right there. Okay, so this is going to be my 5 minus 7i plotted on the complex plane. Okay, so the last thing would be the absolute value of a complex number. So if we have something like the absolute value of 2 plus 6i, again, remember the way you would do this, this is going to be the distance between this number and 0, or the origin on the complex plane, okay? So your distance formula normally is what? It's the square root of, you have x sub 2 minus x sub 1 quantity squared, plus you have y sub 2 minus y sub 1 quantity squared. Well, one of the points is at the origin, right? So it's 0, 0. So this is 0, and this is 0. So this is 0, and this is 0. So really, I can simplify this and say the distance between this guy and the origin is the square root of, drop the x sub 2 and just say x squared, plus drop the y sub 2 and say y squared, okay? Now, in the terminology of complex numbers, instead of saying x squared, I'm going to say a squared. Instead of saying y squared, I'm going to say b squared, okay? So what I'm going to do is say that the absolute value of some complex number, let's say a plus bi, is equal to the square root of a squared plus b squared. So this is the square root of 2 squared, okay, 2 squared, and make that better, 2 squared, plus this guy would be 6 squared. So this is the square root of 4 plus 36, so it's the square root of 40, okay, which is square root of 4 times square root of 10, which in the end, let me get rid of this so I have some room to write this. In the end is going to be 2 times square root of 10. So this equals 2 times square root of 10, okay? If you want to see this graphically, you could plot this guy, this 2 plus 6i, on the complex plane. So 2 units to the right on the real axis, 6 units up on the imaginary axis. So that gives us this 2 plus 6i, so that's this guy right here. And then basically what I'm doing is just forming a right triangle, right? So this guy right here, okay, is going to be my hypotenuse. That's what I'm looking for, is the length of that guy. So this is the absolute value of the 2 plus 6i, the absolute value of that complex number. And again, if you look at this distance from here to here, let me circle this in a different color. So let me use this color here. So from here to here, well, this is 6 units, right? So this is 6 units. Let me put a 6 there. And then if you look at the distance from there to there, it's 2 units. So again, with the Pythagorean theorem, it's 2 squared plus 6 squared is going to be equal to, which in this case would be the absolute value of 2 plus 6i, okay? We might as well just say that's squared, right? The a squared plus b squared equals c squared. Well, if I take the square root of each side, well, then I'm back to my formula, okay, which gives me the square root of 4 plus 36, which is the square root of 40, okay? And again, we just simplify that, so we know that in the end, the absolute value of this 2 plus 6i is going to be 2 times the square root of 10, okay? So you can see that graphically or just from using your formula.